This is a quadratic. It's a polynomial in x whose highest power is 2. If you graph it, you get a parabola, and in school we learn that these 2 points where the parabola cuts the x-axis are very important. These are called the roots of the corresponding quadratic equation x squared plus x minus 6 equals 0. These roots, it turns out, are so important that in school you'll probably learn 4 or 5 different ways of finding them. The absolute simplest case allows you to find them by just taking square roots. The real stuff usually starts out with identifying the roots on a graph. Then we spend a while learning to factor. We can factor this guy here into x plus 3 times x minus 2 equals 0 and use a zero product property to determine x equals negative 3 and x equals 2 are the solutions. Then there's completing the square, which always works, and so this method is generalized to create the quadratic formula, the unwieldy spell that is cast by bright students all over the world each day. But what if I told you there's another top secret method that was first used in the 1500s to approximate the square root of 13? What is the square root of 13? 3 squared is 9, so clearly 3 is too small. However, 4 squared is 16, so 4 is clearly too big. So it's easy to see the square root of 13 is between 3 and 4. But what if you wanted more precision for your approximation? In 1579, Italian mathematician Raphael Bombelli published a new edition of one of his books. And what an edition it was! In it, he showed a new method for approximating the square root of 13. And his approximation looked like this. 3 plus 4 over 6 plus 4 over 6 plus 4 over 6 plus and so on. Now, I said approximation, so you might be wondering what's with the equals sign. Well, as you can see from the pattern in the ellipses, this expression can be carried out as far as we like. If we compute only the first convergent, as it is called, the approximation is 3. We stop at the first plus sign. If we go 2 steps, we'll go up through the second plus sign, so 3 plus 4 over 6, that's the second convergent, which is about 3.67. For the third convergent, we go through to the next addition sign, so the third convergent is 3 plus 4 over 6 plus 4 over 6, which is 3.6. And if you grab a calculator to compute the square root of 13, you can see the approximation is pretty close. And we can get arbitrarily close to the true value of the square root of 13 by simply carrying out this computation further and further, hence the equals sign. The square root of 13 is the limit of this expression. If it was carried out infinitely, it would equal root 13 exactly. If you're a fraction hater, this probably looks like a nest of spiders to an arachnophobe, but this isn't a spider. It's a continued fraction. And yes, these glamorous non-spider expressions can be used to solve quadratic equations. Let me show you how. To understand how a quadratic equation can be solved with an infinite stack of fractions, we should first see how any value at all can be expressed as a continued fraction. I've told you that this is true, but let's actually work out an example from start to finish. Take 101 over 43, for example. We're going to write this as a continued fraction. We can all agree that 101 is 2 copies of 43 with the remainder of 15. We then essentially follow an ancient technique called Euclid's division algorithm, which involves taking the quotient and the remainder and repeating this process. So the quotient 43 is equal to 2 copies of 15 with the remainder of 13. And then 15 is equal to 1 copy of 13 with the remainder of 2. 13 is equal to 6 copies of 2 with the remainder of 1. And 2 is 2 copies of 1 with the remainder of 0. 0. For our continued fraction, we just need these first 4 equations with non-zero remainders. And here's the trick. Remember, we're trying to write 101 over 43. So we're going to take this first equation and divide both sides by 43. That way on the left, we'll have 101 over 43. We'll have this. And if we do that, what do we get on the right? Well, 2 times 43 divided by 43 is just 2. And then 15 over 43 is 15 over 43. Then we're going to rewrite 15 over 43 using the second equation. Take the second equation and divide both sides by 15. So on the left, we have 43 over 15. And on the right, we have 2 times 15 divided by 15 is 2, and 13 divided by 15 is 13 divided by 15. Now, to plug this into our expression, well, we need 15 over 43. This is 43 over 15, so just flip it. If this is 43 over 15, then 15 over 43 is 1 over all of that. So then this is also equal to 2 plus 1 over all of this, 2 plus 13 over 15. And then we just do this again, rewriting 13 over 15 with the third equation. Divide both sides of the equation by 13. So on the left, we have 15 over 13, and on the right, we have 1 plus 2 over 13. Then to get 13 over 15 like we need, we just put all of this under 1. So we can rewrite this expression again as 2 plus 1 over 2 plus 13 over 15, which is the same as 1 over 1 plus 2 over 13. And then we do this one more time to rewrite 2 over 13 using the last equation. And that, my friends, is how you write 101 over 43 as a continued fraction. If you want to improve your math skills to deal with continued fractions and other creatures of the infinite, check out today's sponsor, Brilliant.org. At the root of continued fractions is the limit process, which is studied in calculus, and you can begin to learn and appreciate this beautiful subject with Brilliant's interactive calculus course. The lessons will take you from rates of change and the derivative all the way through the fundamental theorem, sequences, series, and of course, limits. There are so many other great courses too, like visual algebra and programming with Python. Each course builds your understanding from the ground up with intuitive visual lessons, and you can access them on your computer or through the Brilliant mobile app to make building a daily study habit easy. To learn for free on Brilliant, go to brilliant.org/wrathofmath, scan the QR code on screen, or click on the link in the description. Brilliant's also given Wrath of Math viewers 20% off an annual premium subscription, which gives you unlimited daily access to everything on Brilliant. Constructing this fraction was pretty easy, but wait, this isn't a continued fraction. This fraction ceases. This is a ceased fraction. Well, actually, a continued fraction can be finite or infinite. This one is finite because it's a rational value. On the other hand, the square root of 13 isn't rational, and so its continued fraction representation is infinite, hence the ellipses. Regardless, we see a pretty simple technique here for representing a given rational number as a continued fraction. But how could we use this to solve quadratics? Not only could a continued fraction be infinite if the solution is irrational, but the whole point of solving a quadratic is we don't know the number we're trying to express. So how could this possibly work? Let me convince you with a simple exercise. Let's say we wanted to solve x squared equals 2. We could just take the square root on both sides, but you know math class, that's too easy. Instead, let's subtract 1 from both sides. Now, on the left, we have a difference of squares, so we can factor that as x plus 1 times x minus 1. Then we're going to divide both sides of this equation by x plus 1. So we have x minus 1 equals 1 over x plus 1. Now we'll just add 1 to both sides, and I'm going to flip the order of the 1 plus x here. Of course, doesn't matter because it's just addition. So x equals 1 plus 1 over 1 plus x. What good is this, I hear you asking? Don't we need x all by itself? Not so, my pessimistic pal. We know all that we need. You might think this is a problem because we have x on this side of the equation. But what is x? Well, it's 1 plus 1 over 1 plus x. So that means x is equal to 1 plus 1 over 1 plus x, which is 1 plus 1 over 1 plus x. And of course, 1 plus 1 is 2, so we can rewrite this. And now I know that x is 1 plus 1 over 2 plus 1 over 1 plus x. 1 plus what? 1 plus x. What's x? 1 plus 1 over 1 plus x. So we replace it again. Again, we could combine the 1 and the 1 to 2, but there's no way that's going to fit on my paper if I write another line. Point is, we can repeat this process as much as we like, pushing the x further down and further to the right in the denominator. Of course, we're always going to get this pair of 1s combining to 2 every time we replace x with this initial expression, so in total, we conclude that x is equal to this continued fraction. 1 plus 1 over 2 plus 1 over 2 plus 1 over 2, and so on. And what about the second root of the quadratic? Well, hey, the graph of a quadratic equation is symmetric, so knowing one root is as good as knowing both. Understandably, one might wonder why this would be preferable to just finding the solution the normal way. Well, what if we actually want to know what the solution root 2 is? How do we actually calculate it? If all we have is root 2, then we need a technique to extract the root, as it is called. On the other hand, with the continued fraction, the method of calculation is laid bare. To actually calculate the solution, just do 1 plus 1 over 2 plus 1 over 2 plus, and so on. We can compute this as far as we like to calculate the solution's value as precisely as you please. We just do 1 plus 1 over 2 plus 1 over 2 plus, and so on. We can calculate this as far as we like to get the solution as precisely as we please. And just like that, you've seen a new way to solve quadratic equations. But this may have seemed like a fairly contrived example. Quadratic equations aren't usually so simple. So the question is, how can we tackle a standard form quadratic like ax squared plus bx plus c equals 0 using the ultimate weapon of continued fractions? Well, it's actually a breeze. First, we want this to be a monic polynomial, which means the leading coefficient should be 1. So we'll just divide everything by a. Remember that a can't be 0, otherwise we don't even have a quadratic equation. So dividing everything by a is totally permissible and really cool. Now we're going to move everything away from the x squared, so we'll subtract all that junk to the other side, giving us x squared equals negative b over ax minus c over a. Now you need to understand that negative b over a and negative c over a are just numbers, and since they're arbitrary, there's no reason we need to write them in such a grotesque fashion. In other words, we're totally free to just relabel these things, and I'm going to call them b and c. So then, to solve a general quadratic equation with continued fractions, we're just going to assume we have a quadratic in the form x squared equals bx plus c. Any quadratic that isn't in this form can easily be put into the form. Now, this should be familiar territory. On the left, we have two factors of x, so we're going to go ahead and divide both sides by one factor of x, giving us x equals b plus c over x. And you can see where we're going now. C over what? X? Well, x is just b plus c over x. So this is b plus c over b plus c over x. Wait a minute, c over what? X? X is just b plus c over x. And that means that this is equal to b plus c over b plus c over b plus c over x. Wait, c over what? X? And well, you can see how this process continues. We thus solve for x as this continued fraction in terms of b and c. It's b plus c over b plus c over b plus, and so on. Could it really be that simple? No, it's not. It's easy to say the continued fraction method gives you one root, and then you can just reflect it across the axis of symmetry to get the other root, but that's ignoring all the possible other situations. What if the quadratic only has a single root? What if it doesn't have any? We took this equation and divided both sides by x. What if x is 0? We need to be aware of these possibilities so that we don't overextend our method and make false conclusions. For an example of how quickly disaster can strike, let's try our continued fraction method with x squared minus 2 equals 0. Putting it in our preferred form of x squared equals bx plus c, we could rewrite it as x squared equals 0x plus 2. B, of course, is 0, c is 2. We can then blindly apply our continued fraction formula and get that x equals 0 plus 2 over 0 plus 2 over 0 plus, and so on. And if we then look at the convergence to approximate the root, well, at first we would just have 0, that's going up through the first addition sign. Then we go up through the second addition sign for the second convergent, which is 0 minus 2 over 0. Oh no, that fell apart mighty fast. The convergents alternate between 0 and the undefined non-zero number over 0, which you may regard as infinity if you're feeling frisky. Of course, the problem here is that b equals 0. This causes the continued fraction formula we found to totally break. This is despite the fact that we can solve this equation with continued fractions. Remember, we did so earlier. But just applying this formula doesn't work in this case where b is equal to 0. In general, if we have x squared equals c for some positive real number c, we can use the same strategy we did with x squared equals 2. Just pick a positive number p with a square that's less than c, subtract p squared from both sides of the equation, then factor, then divide, then add, and then from here you can construct the continued fraction. So if b is equal to 0, we can still use continued fractions as long as c is positive. We just need to use an alternative strategy. On the other hand, if b is non-zero, but c itself is 0, then one of the roots will be 0, so you might think that our method wouldn't work due to the division by x. But in fact, the method works just fine, and you'll see why later. Okay, so as long as b is not 0, then we're good to check the other potential problems. In your algebra class, you should have learned about the discriminant. It's the b squared minus 4ac that lies within the square root of the quadratic formula. With the discriminant, we can discriminate between the different situations we encounter when solving quadratics. If the discriminant is equal to 0, then the plus or minus in the quadratic formula isn't really doing anything, so there's only one real root and our continued fraction converges to it. On the other hand, if the discriminant is less than 0, well, you can't take the square root of a negative, so in that case there are no real roots, and the continued fraction will diverge, much like we saw in the situation where b was equal to 0. It will oscillate with this chaotic behavior. And finally, if the discriminant is positive, then there are two real roots, and the continued fraction will actually converge to the root with greatest magnitude. This is why one root, being x equals 0, doesn't actually present a problem. Due to this rule, the continued fraction is always going to converge to the root that isn't 0. Hence, this division by x in that situation isn't actually a division by 0. We're dividing by whatever the greater root happens to be. For an example of the continued fraction converging to the greater root, we previously saw how this quadratic equation had roots of -3 and +2. If we put it into the form to apply our continued fraction formula, b would be -1 and c would be +6. And you can try computing the convergence of this continued fraction yourself. You'll see that it converges to -3, the root with greater magnitude. It's kind of like the greater weight of the higher magnitude root pulls the continued fraction towards it. In fact, it's really like that when we consider the rate of convergence. We suggested earlier that this continued fraction converges to the square root of 2, and that one reason this is useful is it actually gives us a way to compute the square root of 2. But this is only useful if the continued fraction converges to root 2 relatively quickly. In theory, it could become a very good approximation eventually, but if we have to extend the fraction for a billion denominators before we get a decent approximation, then it's really not so useful after all. So let's look at one more interesting facet of these continued fractions before we go. The equation x squared minus 3x plus 2 equals 0 has the roots x equals 2 and x equals 1. Thus, the continued fraction would converge to x equals 2, the root of greater magnitude. If we construct the continued fraction and calculate up through 3 divisions, we get about 2.067. This is an error of 3.3%. Now, take the equation x squared minus 6x plus 5 equals 0, which has roots of x equals 5 and x equals 1. The continued fraction will converge to 5. And if we compute the continued fraction up through, again, 3 divisions, we get about 5.0064. This is an error of just 0.128%. So look at that. In both cases, we computed the continued fraction up through 3 divisions, but in this one, we got a much better approximation when you compare those errors. And why is that? It's actually because of the ratio of the roots. In this case, the ratio of the 2 roots was 2 to 1. The greater root was twice as big as the smaller root. In this situation, the greater root was 5 times as big as the smaller root. So the takeaway is the continued fraction will converge to the greater root, and it will converge faster the greater the ratio is between greater and lesser roots. Again, greater means greater magnitude. You know, it's amazing it took 1800 years after the Euclidean algorithm for some clever chap to use a similar process to construct continued fractions. But we live now in a time where continued fractions are a well-understood piece of mathematics that have been studied a great deal. And now you can use these magnificent creatures yourself to solve those pesky quadratic equations. You're welcome.
I'm unstable, I'm feeling art to keep the cable cut and unsort the table. If Texas Instruments don't reply, well, I think this time it might be fatal. Wish to sell my own fake, cause I'm jaded.
Hate the odds that I calculated.
Press and pull and pray and push it all the way through the whole blue
Planet faded.
psychosomatic habits, why you so